Hey guys, my name's Joe, and in this video I'm going to go over everything I learned in my mechanical engineering degree. So we're going to pretty much go chronologically with this. So here's a rough overview of all 4 years. So in year one, gen eds, generic calculus and physics courses run by those relevant departments. And then you have an intro to engineering course, a few different random classes for that where they just go over a bunch of random basic things. Then year two, you get a little bit more into the actual mechanical engineering stuff, intro to structural analysis and mechanics, and an overview of CAD class, advanced calculus, and thermodynamics. Thermodynamics being power cycles like power plants or car engines and stuff. Then year three is more advanced mechanical or structural analysis, heat transfer, mechanical design, using a lot of these concepts that were gone over before. And then year four, you spend most of your time with your capstone project, and otherwise there is a bunch of experiments you do in one class, and might also do some electives that year. So starting with year one, so you do calculus 1 and 2, calculus 1 integrals, calculus 2 derivatives, then physics, and then intro to engineering courses, gen eds, which we'll go over all of this now. So calculus 1 is when you go over derivatives, which is these equations right here. So if you've got this function x squared plus 2x, and then you take the derivative of it, which in this case would be 2x plus 2, where you just change the exponent of both of these expressions. And then, so the derivative, what it is it's pretty much the rate of change. It's the change of y over the change in x. And so it's basically the slope of the function at any given point. And so that's why 2x plus 2, if we were to take the derivative of this, we would have a line for just 2x plus 2, because that's the slope of this function at any of those given points. Regarding integrals, it's the opposite of derivatives. You'd have this kind of symbol right here, where you're going from 0 to 10, what's the area under the curve of x squared plus 2x. And then it's a lot more complicated because you have to, instead of just lowering the exponents of each of these expressions, you have to, in a lot of cases, do some more fancy things. But yeah, calculus 1 is the easier one. Then you also do physics 1. So you go over, physics 1 is the mechanics, whereas physics 2 is electricity. And going to more focus on mechanics here because this is the mechanical engineering degree. But you got your kinematic equations, which is all these guys. And if you've taken a physics class before, you've probably gone over motion. The final position equals the initial position plus the velocity times time. Or the final velocity equals the initial velocity plus acceleration times time. And you use some of these equations together in order to determine what's an object's final velocity or an object's final position, if you just use one of them or use multiple of them in conjunction. You also go over force balancing, namely, you talk about gravity acting down, like if this is an object that is resting on top of a table, gravity's pulling it down. And then the force of normal is the equal and opposite force that's pushing it up. So the table pushing the object up. Friction can act toward the side, or for instance, if you push it towards this direction, if you push it towards the right, then friction's going to act towards the left. That's basically how force balancing works, and if it's not accelerating, that would mean that the forces are all balanced together. And then for energy equations, energy, conservation of energy pretty much. So you might start with an object, potential energy due to gravity, which equals to mass times gravity times height. So if you have an object right up here, then you calculate this potential energy. And then by the time it gets all the way back down, when you drop it, then its kinetic energy is going to be equal to this. So let's talk about Intro to Engineering course. This is a lot of just random basic intro topics. You go over, I think, just very basic CAD. We did stuff with breadboards, which is more of an electrical thing, where you plug in some wires into different parts of the board in order to power things. We went over MATLAB a little bit. So there were just a few random things, and there was this kind of dummy project where they had us just do a really basic project and figure out how to handle a team and handle goals, and something that was somewhat realistic. So let's talk about year 2 now. So year 2, you do Calc 3 and then differential equations, and Calc 3 just being 3D version of Calc 1 and 2. Then you do a statics and dynamics course, and then a course that's the introduction to SolidWorks, and then mechanics of materials. So calculus, it's really just the 3D version of Calc 1 and 2. You do derivatives in 3D, integrals in 3D, sometimes directional derivatives if it's just kind of a line. And then differential equations, that's the really hard one, where you might be doing more of like you have to find out what the equation is given its derivative. So if we go back to what we have right here, and if you're trying to find dx dy as a function of something else, then you would find what the function is from the derivative. And then this is one of your first big engineering courses from the mechanical engineering department. And statics and dynamics, you're pretty much building on physics 1. You're doing a lot of these same force and moment balancing stuff, except physics 1, you don't really go over moments. Moments being, in this case, like if you have a rod and a force acting on the rod, it's going to have a moment on it. And so the moment, if there's a moment imbalance, then not only is it accelerating linearly, but it's also accelerating rotationally, like with this guy juggling these these pins. Like, so if the pins are rotating at a constant rotational velocity, then that would mean that the moments on them are also balanced. And then you're also going to go over like whether or not forces and moments, like what's the position final of them using similar kinematic equations and such. And then next after that, in terms of an engineering course, you go over mechanics of materials, or sometimes it's called solid mechanics. And so this is where you get into stress. Stress is, it's basically the force over the area. So if you're pulling on a rod, then the stress in the rod is going to be the force that you pull with divided by the cross-sectional area of the rod. But it gets more complicated because when you introduce things like bending and stuff and torsion, then you have compression on one end, tension on the other when you're bending it. And so there's specific equations for that. And so like in this case, we got torsion of an I-beam. So you would solve for torsion, which is the torque times the distance to the extreme fiber divided by the polar moment of inertia. And then this is the equation for polar moment of inertia, which polar moment of inertia is basically its resistance to bending or resistance to torsion. Yeah, resistance to torsion if it's the more twisting rather than bending. And that's how you solve for what would the stress in the I-beam in just various points of the cross-section be. Then you've also got an Intro to CAD course, which, at least at my university, they used SolidWorks, which tends to be what they start you with. And it's just how do you build 3D models of things and then assemble them together, like what this guy's doing. It's just a simulation or a software where you draw out 3D parts for these, and then you also can put them into 2D drawings. So this was kind of a basic overview of CAD. Another image example is this one right here of what would be a bracket that could have been modeled in SolidWorks. So then you go into a thermodynamics course, which in my program it was called Thermofluids 1. And so it's basically similar concept as conservation of energy, like we talked about in Physics 1, except that you're talking about things like steam cycles or automotive cycles and such, where energy is balanced when you cross it through some kind of threshold that does work. And in this case, we got a power plant that's generating energy using fossil fuels and steam, and then the water is so hot going through it, it has to cool down. So these cooling towers here are letting air out. So this course, we used a lot of these tables, like steam tables or liquid water tables, and saw, okay, what's the temperature? And then that tells us what the enthalpy is, which is just kind of an indirect measure of how much energy per unit is going through. And then what would the temperature be once you get out of the cooling tower? So a lot of different equations for how much work is done by the power plant and the conservation of energy through it. And this is arguably, I think, the hardest course in the entire curriculum. So brace yourself for that. But getting into year 3, similar kinds of structural mechanics stuff, but this course talking more about failure theories. This is plane stress, where you're simplifying stress in kind of an infinitesimally small 3D cube, where there's normal stress in all 3 directions and shear stress in all 3 directions. But if you have like a thin bracket, you could simplify it just to 2D, where it's just normal stress in one direction, normal stress in the other direction, perpendicular, and then the shear stress in the entire element. Then you also go over failure theories, like this is what's called Moore's circle, where there's different stresses with angles, and what's the principal stress that could potentially cause the material to fail. And then you go over a mechanical design course where you're applying all this mechanic stuff to random things like designs of gears or shafts, or the image I have here is pressurized vessels or pressurized pipes and stuff. And so this is an equation for pipe stress, given what's the internal pressure of the fluid inside the pipe and what the inner radius and outer radius of the pipe are. Then you also have a heat transfer class where you go over conduction, convection, and radiation. Conduction being the heat being transferred through a material within it. Convection being basically heat transferred from a fluid to a solid, and then radiation being heat transferred via basically energy rays from especially like the sun or something like that. So like if you have the sun and it's a sunny day on a black street, the street's going to get pretty hot from the radiation. And then in the example of like cooking a steak, for instance, you might have convection from the coals or from the propane that's heating up the bottom of the steak, and then conduction that's causing a heat transfer from the surface of the steak to more the inside of the steak. So there's a bunch of equations to determine what's the temperature on the outside. I mean, they don't go over this exact example. It's more like between fluids and metals and stuff like that, but you might have like a piece of metal and then determining what the temperature on the surface of the metal is given its convection coefficient and what the ambient temperature is and such. Then you also have a control systems class, and they didn't go over this example, but this is a project that I did comparing basically as humans our cycles for making sure we can control our body temperature to similar things in like an air conditioning cycle. So you might have systems going through your nervous system detecting it's really hot and then saying let's activate those sweat glands to cool yourself off, and then a feedback loop. So this was a lot of like functions used for control signals, including feedback loops that can tell the initial system, okay, we need to get hotter, or we need to get warmer, or we need to get cooler, stuff like that. And then in your 4th year, you go over mostly your capstone project, and then also probably catching up on some electives or whatever. But you also have this experimental mechanical engineering course where they take a lot of concepts that you went through in previous years and do a bunch of experiments on them. And in this case, this was one with showing the accuracy and showing how thermocouples work. So this is a diagram of what it looked like. You got ice water, boiling water to calibrate the thermocouple, then sensors, and then programming it to say, like, the ice water is where it must have been 0 degrees Celsius, and the boiling water was where it must have been 100 degrees Celsius, using this kind of equation here to, in the computer, just doing some calculations for that. And then also my team had our capstone project, which took the entire year, which in our case we did a portable water turbine, where we took this big slab of wood, put a generator onto this shaft with a turbine on it that we could just put into a river and hope that it would generate some electricity. And I was working on this planetary gear set that we could use to optimize the amount of rotational speed through the pump, or through the, sorry, not the pump, through the generator, and then that would optimize the amount of electricity going through it. We ended up scrapping this part just because of complications, although in the end it honestly didn't generate nearly as much electricity as it could have. But yeah, this was basically how it turned out and what it looked like. But yeah, so that's pretty much what my entire mechanical engineering degree was. So that's what we've got for today. Thanks for tuning in, and I hope you found it helpful and enjoyable in getting an understanding of the concepts studied in mechanical engineering curricula. Hopefully you have a good idea of what to expect, and also just help you make the decision of whether or not to go into it. And if you found this helpful or enjoyed it, be sure to hit the like button and the subscribe button. And stay tuned for future videos about engineering careers and get the help you need getting into them and getting good ones. Have a good one. Bye.